This is what the traditional GIS stack looks like. And this is what the modern GIS stack looks like. Now, at first glance, it can seem like chaos, dozens of tools and layers and systems. And when you understand these basic layers, there's only a few key skills that you really need to master to make it all work together. So in this video, we're going to break down the modern geospatial stack, how it's different than the traditional geospatial or GIS stack, acknowledging that it's overwhelming at first, but getting into the key insights and layers that you need to understand how to make it fit for the work that you do. So let's take a look at this diagram and we're going to break down each part of it. First, let's go into the file formats and understand how things have changed. Now, in the traditional GIS stack, you're probably using a number of different things. You might be using shapefiles, GeoJSONs for vector data, a number of different formats for raster data, and then things like geodatabases, layer files, and maybe some file formats that store maps in ArcGIS or other systems. That's changed and it's moved into this cloud-native geospatial formats. Now, if you hear the word cloud, that may be a little confusing. You don't actually need to use the cloud to make use of these formats. The key advantage of using cloud-native formats is that they can sit on what's known as a storage bucket, which you can see that section over here. Storage buckets are just like, file systems in the cloud. These are systems that store literally everything on the web, from images and videos, PDFs, you name it. They all are backed up by cloud storage systems. Now, the reason they do that is because they're incredibly scalable, they're cheap, they can deploy to multiple different regions of the Earth, and importantly for spatial data, allows you to stream that data without downloading massive files. So if we imagine the case where we have a very large file that's sitting on a cloud server, in the traditional world, we would have to download that entire thing and move it to our computer or system to work. With GeoParquet or cloud-optimized GeoTIFFs or some of these other formats you see here, we can actually leave that data there and only retrieve the parts of it we need. Sometimes we don't even have to download the file at all. We can just query that remotely and pull that into our system. And these behave like modern replacements for things like shapefiles or feature services or anything like that. And there's a few different ones you want to break down. GeoParquet is the vector version format. I have a video about that here if you want to learn more about that and why it's important. There's also cloud-optimized GeoTIFFs, which are often paired with spatiotemporal asset catalogs, which are kind of like a service that allow you to search and understand what's inside of these different files. Zarr is another file format that is also included. It's climate-based data. So if you're familiar with like NetCDFs, it allows you to access that array and time series data for things like, wind and rain and all these different measurements and climatology measurements. It's not quite a raster because it's not like an image, but it kind of embeds it in the same grid format, but it allows you to do that very efficiently. Now, there are also formats like cloud-optimized point clouds, as well as PM tiles, which is like a tiling service, or if you think of it like a feature layer, that basically lives on the cloud storage and you don't need any server or other infrastructure to run it. It's really advantageous and very scalable. Now, to make all of that work, there's a lot of optimizations built into it. If you want to learn more about it, here's a great guide from Cloud-Native Geospatial Foundation that goes into that in greater detail. And of course, we couldn't store or do anything with this data without cloud storage. There's lots of different systems to do that. There's the major cloud provider services like AWS S3, Google Cloud Storage, Azure Blob Storage, as well as other ones like Cloudflare, Wasabi, even DigitalOcean all have storage services. There's a really great library that was put together by Development Seed that is called ObStore that allows you to move data back and forth really efficiently. But you can also use different libraries in Python to basically take files that you have and write them to the cloud or read them from there. But this is literally just storage, right? It allows you to do it very cheaply. It allows anyone to access it. It gives you permissions, all these different things. But on top of that, there's no organization within that. When you change a file, just like you would on your computer, if you delete it, it's kind of gone forever. So how do you embed history or different metadata on top of that? And that's where catalogs come in. Now, catalogs add the intelligence on top of your storage, that things like search, histories, schemas, versioning, even access rights and stuff like that all live within these catalogs. And there's a few different ones you want to be aware of. One is called the spatiotemporal asset catalog, which I mentioned earlier. That is primarily living with raster data that allows you to see different parts of the file, allows you to see when it was created, where it was created, like the exact position on the globe, different information about the bands inside of that metadata, as well as things like cloud cover and then the time it was taken. So it has all this rich history, and you can kind of search using this Stack API to say, I just care about images in this time frame that maybe had 5% or less cloud cover. It's a very powerful tool for searching this data. And lots of different providers have adopted this format, as well as different cloud providers like AWS actually use this as well. Now, Iceberg does that, but for tabular or vector data. Now, it has a lot of key advantages on top of a Parquet file schema. It adds advanced partitioning, which basically makes things faster and more searchable. It allows you to add history, so you can append the data, overwrite it, and actually go back to different snapshots in time. So as the data changes, you can see that. You can add schema evolution. There's different sorting and organization of the data. And effectively, it allows you to connect it to other sources. Lots of different query layers or different systems are adopting Iceberg as a specification. So we'll talk more about that, but basically you don't have to transfer the data out, and you get the benefit of all this history that's coming with it. So it's ACID compliant, so there's lots of database-like features like that. It's not a full transactional database. We'll talk about that in a minute, but it's incredibly powerful, and I think it's one of the things you're going to seeing a lot about as it starts to get adopted across the stack. Now, for some of the array-based formats, there is a library called IceChunk that's put together by Earthmover. They basically add that cataloging service on for the array-based data. So that's another one to keep an eye on how that develops. It basically allows you to do a lot of the same things Iceberg does, but for that array-based data in Zarr. So now that we have this very foundational piece of the stack built, how does this build up and how do you actually interact with the data? So the first is going to be kind of the transformational layer, right? You see these two pieces on the side here. We're going to quickly talk about those because they sit across multiple different components. When we talk about transformation, that might be for converting or cleaning data. There's lots of tools here that are both geospatial specific, like GDAL. It's this very interoperable layer to do file transformations and some lightweight processing. It sits in pretty much every tool inside the geospatial stack, apart from Geos, which is another library, or JTS, which are some of these very foundational libraries within geospatial. But GDAL allows you to actually do that and is embedded in lots of different tools. So if you're transferring file types from one to another, you're probably interacting with it in some way or another. There's a full video about it here if you want to check that out. There's also some of the spatial indexes, so things like H3 or A5, that allow you to translate geospatial data into a spatial index. And if you want to learn more about that, here's a full podcast on A5 here I did with Felix Palmer, who created that system. And there's other tools that are kind of known as like ELT or extract, load, and transform that allow you to move data from one place to another. The two most important ones are like DBT and Airbyte. There are some other ones here that you can take a look at, both proprietary and open source. But effectively, they're taking data from one place, maybe a storage bucket, and moving it into another system, right? It's basically an apples to apples. And DBT adds some transformational pieces there, but effectively it's data movement. You can look at all these things as translating from one form to another. And you can do that kind of anywhere in the stack you might need to, but there's different ways to do that as well. That's kind of why I have it as a vertical piece over here. Now on the right side here, we have orchestration. That's allowing you to basically keep the process running and define how you want things to happen. So Airflow is probably one of the most relevant ones here. It's been around for the longest. It's an Apache project. There are other ones like Prefect and Dagster, which are commonly used as well. So it really depends on kind of how you want to use that. I personally use Airflow because it has a lot of really great features in it. Now the way to think about this is it's kind of like a modern FME, right? It's all based in Python, so you can kind of script out these flows, or what they're called DAGs, that allow you to build these different steps that you want. Even if you're in a desktop GIS, you can kind of think about it like a model builder, right? But it's all scripted in Python. It's very scalable. There's lots of features and functionality that you can do with that. There's actually a full podcast here I did with the team from Airflow and Astronomer. If you want to check that out, that's another good place to learn more about Airflow. So now we have these tools that allow us to transform data, orchestrate it, and our base data. So now what we need to do with it are three different things. And these three different functions, they may look very similar, and you may use different tools here to do one of these different pieces, but I'm going to make some recommendations here on how you split these out because I think they are all separate tasks. And in the modern data space, this is how things are organized there as well. So the first, we have the processing layer. This is where you do distributed spatial computation. This is where it's not just for large data, but if you have to kind of orchestrate across complex analysis or batch data or do, basically large areas, the data scale or big data piece, it can kind of be debated how that fits, but it's basically for these larger tasks, right? I break apart larger in a few different metrics. It could be the number of rows, the complexity of the geometry, the granularity of the data. All those different things are kind of how you might measure that. But effectively, it allows you to do that in a very scalable format. There's a few different tools here that you can use. Apache Sedona is one that's probably one of the most popular and well used. It has over 50 million downloads, and it basically connects into Apache Apache Spark, which allows you to have that distributed computing. Wherobots is a cloud version of that builds it all in and adds some extra optimizations, but effectively that allows you to do that. And it connects in really well to things like Airflow, as well as Apache Iceberg. So you can create, tables with Parquet files, you can orchestrate it with Airflow, and then you can have the ability to create these connectable catalogs with Iceberg and different systems like that. Databricks also added some spatial SQL functionality here at the end of 2025, so they're adding some different pieces here as well as going across the stack as well. Dask is another one that's been commonly used for raster or climate data as well. It's another distributed, processing. There's a cloud version of that called Coiled. So there's different versions of these things as well in different layers. If you want to learn a little bit more about Apache Sedona or Sedona DB, which is a lighter weight version of that, you can check out these 2 videos up here that will explain a little bit more about those pieces as well. The key for the processing layer is if you have these large processes, you have a whole file that you need to kind of do some processing, maybe some transformations, a number of different things here. It's hard to say specifically what that might be, but anything like large scale raster algebra. Maybe you need to do a raster to vector join. Maybe you need to do a buffer join or some transformations or clippings at very, very large scale. That's usually where these tools sit. Now, you may have done some of these different things in PostGIS before, and that's because PostGIS is another database system that does very similar things, but also has some limits on scale. The main reason there is that the processing layer splits out the compute and the storage. The storage is coming from these files at the bottom, and you are using your processing or computing layer and bringing it down to that. In a transactional database, that's basically put together, right? If you need to store more data, you need to add more space, and if you need to add more computing power, you need to have that up and running all the time. The processing layer does that on demand, which makes it advantageous and cost effective. So let's talk a little bit about the transactional layer here. PostGIS is a database and it is built on top of PostgreSQL. It's an extension of PostgreSQL. It's been around for a very long time, since the early 2000s. It's well tested and has probably the most spatial functionality out there. And it's really great for quick updates. If you need to do like editing based workflows, if you have multiple people contributing to a database, it can kind of centralize your data there. And it's great for smaller queries and things like that, but is known as an OLTP or online transactional processing database. So when maybe you have an application where someone's submitting something or inserting something, you're making changes like an update, maybe you're editing a geometry, PostGIS is a perfect choice for that. And it can do analytical queries. It has been used for that for a long time. But like I said, there's a certain limit of scale of where that is, and it's still kind of being figured out where that is and when you need to add processing plus transactional. But for right now, you kind of have to feel that out a little bit to say, hey, this is taking too long, and you want to pair the processing with the transactional as well. So that's something to think about, but PostGIS is really like a foundational tool in any spatial stack. I highly recommend using it. And for processing, you can actually process data and push it into PostGIS. You have it alongside your transactional data, but the PostGIS connects up to a lot of these other scales where maybe you're doing some processing, you want to push updates and things like that. PostGIS is a really good place to do things like that. Now, on the right-hand side here, we have the Analytical Database, or OLAP, Online Analytical Processing. And these things will kind of sound familiar, but they each have their specific role inside of the stack here. And online analytical processing, that's kind of also known as like data warehouses, or different systems like that. They allow you to ask analytical queries, and they kind of grew out of this space of companies that had a lot of like historical data or like computer-based or computer-generated data. So if you think of something like Netflix, where there's all these interactions that are happening where people are clicking on different movies or, their viewing history or stuff like that, you have these very long history tables, and someone wanted to aggregate them to get, reports out. There's things like, how many people are watching, this specific show or this specific genre during this week or compared to last week, and how are viewing trends and stuff like that. It allows you to ask those questions very efficiently. It's really built to do those types of things, long data and aggregated views or time series based kind of analysis. And then those workflows are brought up to maybe a data science layer, maybe a business intelligence reporting, something like that. Now, they have added spatial functionality over time, and they're very powerful and scalable. So it kind of made sense to just like, hey, let's do some of our spatial processing there. The tricky part of the give and take there is that these OLAP systems are on-demand querying. So if your query isn't optimized really well or specifically, it can potentially cost a lot of money to do these things there. So you do have to be aware of that, and spatial functions aren't always fully optimized. So usually a workflow will look something like this. Maybe you have your processing layer that does the batch processing and heavy lifting, moving that into an Iceberg layer that is readable, and all these OLAP systems read Iceberg, so it can immediately connect in. And then maybe you have other organizational data there that you want to join in or do as an aggregation. You kind of have this analytics ready data set that comes out of the processing layer that can also be brought back into the transactional layer, or that transactional layer can feed data into the processing layer or over into the online analytical processing as well. So you kind of have this interconnection here. And it's kind of the biggest thing you need to think about is how to strategically use your compute here. Compute, think of it as a sparse resource that you want to preserve and use efficiently, right? That's basically how you want to do this. So that's really how you can set this up to be efficient as possible. So how does this compare to the traditional GIS paradigm? Well, in the processing layer, you might have used different tools, maybe even your desktop. That's where things started to get a little bit, bogged down, or you saw the spinning wheel of death. When you had that happen, that's generally where a processing layer would come in. Those processes that were heavy and took a lot of time, you might want to move that into a processing layer. For the transactional thing, that would be something like an Esri server where you're pushing updates or storing data. Maybe that data would be coming from one of the field collection devices or some of those different tools. That's where data for PostGIS would generally write into, or the transactional layer. For the analytical layer, that's still kind of a new one. It's kind of feels like another big data piece, but if you're doing large scale point and polygon joins and aggregations, that's kind of what the analytical layer would be in that case. So it's like these things existed before, there's if you had a geoanalytics toolbox or something like that, there's different ways that these would be used, but effectively, if you can orchestrate these three pieces and make them work really well together, you can have something that's incredibly powerful, scalable, and very cost-effective at the same time. Sorry, one last note on the online analytical processing. I didn't mention some of the services there. Those are different things there's cloud services like BigQuery, Snowflake. Like I said, Databricks has a version of this, like a warehouse, or Amazon Redshift is another one. There's also open source tools that you can use, things like Sedona DB, which is a single node local service that is provided by Apache Sedona to do very similar analytical queries. Things like DuckDB, as well as MotherDuck, which is a commercial service based on DuckDB. So there's different ways to do that online analytical processing. Okay, so now that we have all our different data, we can bring that into the tools layer, right? And this is where I call the application layer at the very top. This is where you're serving data and doing different things like that. So in the first, we kind of have our analytics layer. That's where you can actually, visualize, do some maybe lightweight processing or things like that. You'll generally be connecting into data for the OLAP side or maybe the OLTP side. So you'll see a lot of these connect to these SQL databases. Same on the GIS side as well, but specifically within this analytical layer. So that's tools like Descartes, which is based on Kepler-GL, obviously Kepler-GL as well. There's different tools that are coming out from Foursquare Studio. Carto's ones that has been around for a long time. So there's lots of different choices here in terms of these analytical tools that can kind of create dashboards and things like that. You can think of them kind of like business intelligence tools, but for spatial data specifically. There's also some business intelligence tools specifically that have really good functionality. The one I really like is Apache Superset. There's a cloud version of that called Preset. I did a podcast interview with those folks here if you want to check out more about that. Now moving into the GIS layer, this is where you can connect it into a desktop GIS system. Things like QGIS, obviously ArcGIS Pro, have increasing connections, especially into the database side, as well as the online analytical processing. So they accept connections into things like BigQuery or maybe DuckDB or PostGIS. This is a really great way to keep an existing GIS workflow, but connect to a modern database system on the back end, right? It allows you to do that in a little bit more of a scalable way. Now, again, of course, there's the Python ecosystem. There's lots of things from GeoPandas to Rasterio. If you're doing machine learning, you can use TorchGeo, as well as many other libraries here as well. Two I always like to call out here are the GeoAI library and LeafMap. Those are built by Dr. Qisheng Wu. Really great libraries that embed a lot of these technologies as well. But again, you can call out to some of these layers directly, either the database side, the processing side, all these different places allow you to that scalability and integrate in very easily. There's also been a wave of new cloud GIS tools that have really added some extensibility and also connection into desktop GIS tools. So if you call out here, Felt allows you to build web maps, but also interoperably connect with QGIS. Adds a lot of really cool functionality there. Atlas is another cool one that allows you to do a lot of different things, create some really great web maps, also kind of fully featured applications as well. And NextJS is another good one that also allows you to do very similar kind of, GIS feeling workflows. And then finally, we have the application layer. That's where you're building custom applications, either web or mobile, that are showing and displaying your map data. Now, one of the biggest of these is Mapbox. They allow you to actually create web maps, build them within JavaScript frameworks, and also within mobile applications. That comes everything with like the base map, the styling, all the different pieces there, but as well as a bunch of other things where you can include like location data services, search, lots of different stuff there, traffic, places, you name it. There's a lot of different tools that allow you to do that there. You can also bring in layers from DeckGL, which is like a web visualization framework that allows you to do a lot of different scalable visualization types, as well as MapLibre, which is an open source toolkit that allows you to build web maps with lots of different things like PM tiles and stuff like that. So there's lots of different ways to actually build these custom applications. And again, you're drawing from data that you've already used from the bottom of the stack. And for all these tools, actually, you're drawing from different places within its data. Once you've done all the heavy work with the data layer, it can become a lot easier to connect it into these different tools rather than trying to shove a lot of the processing or the transactional stuff up into that layer, which we've done in the past, and that can get a little bit tricky. So again, if you're coming from a traditional GIS background, there's lots of things that will seem familiar here. Things like, dashboarding tools and things like that, web applications and web development with JavaScript. There's Python packages and layers here as well as your traditional GIS stack or web GIS stack. So this is kind of where things will be feeling a little bit familiar. And all these pieces at the bottom, all the stuff we've been talking about earlier, really support all this stuff in a modern environment. And I think that's one of the paradoxes in geospatial is that it feels like you have to be a jack of all trades. And that's definitely not the case. In fact, when I strip away all of these different pieces, there's only a few things you really need to learn, right? You just need to learn a few pieces and you can work across a lot of these different pieces, and that allows you to build your goals and what you actually want to do. So in this next video here, I'm going to break down the 4 essential skills that you need to master this stack. There's really 4 in total, and we're going to break that down in this next video. So if you want to jump over there to see what you actually need to learn, click right up here and I'll get you over to this next video in the series.